we go. Okay, so we're gonna look at chapter 8 at least through section 6. And if things are running smooth, we might just knock chapter 8 out today too. But we do want to leave enough time to do the lab. The lab is really not that difficult if you had a chance to read it over, I hope. Is Boyle's law, which I described last week during the chapter 7 lecture. Pressure volume relationship. And it's a really simple lab. Okay. So, talk about solutions. One of the handouts was a chart that describes solubility. So you definitely want to have that one. It's got the gradient boxes. Yeah. Okay. It'll be in the, it's one of the slides also. Let's turn this on. Here we go. Okay. So let's take a look. Turn that off for now. Okay. All right, so if we make it up through 6, we're going to talk about concentration units up through molarity. We'll definitely get that far. All right, we talk about mixtures at the very beginning, right? Homogeneous mixture, another word for homogeneous mixture is a solution. And we have different types of solutions. They can be combinations of what we normally consider a solution is a little bit of solid dissolved in a liquid, like sugar water, salt water. But solutions can be any kind of mixture, as long as it's homogeneous. Liquid is like alcoholic beverages, ethanol and water, and then other stuff. Gases in a liquid, like all pop, is a solution. Actually, it's more than just carbon dioxide and then there's sugar, unless you drink diet drinks. And then they put something else in there that's just as deadly, but not as sweet. Gases and gases, that's a special case. When you have 2 or more gases mixed together, you always get a solution. I mean, no exception, they're always a solution. And it stands to reason because there's so much space between the molecules. I mean, there's room for everybody. So gases are always solutions. You can even have solids. Brass is a solution of copper and nickel. Of course, you can't just put 2 blocks of a copper block and a nickel block and make a solution of them. You got to melt them first. And then once they re-solidify, you have a solution, a solid solution. So when we talk about solutions, there are the major components and the minor components. The major component is the solvent. And there can only be one solvent in a solution. You can have a whole bunch of solutes, the minor components, but there's only one solvent. And for to make things not so complicated and difficult to deal with, the major component is the one you start with as the major component, which in our case, most of the times we're talking about aqueous solutions. So water is the solvent. But there are some solutes that are so soluble, there's so much that will go into solution. If you keep adding them, eventually you'll have more solute than you do solvent. Table sugar is that way. You can have a solution that starts out with a little bit of sugar, and eventually you get, I don't know, 80%, 90% sugar in solution. So, and if you've ever made your own hummingbird juice, it's usually 50-50, half water and half sugar. But it'll go higher than that. And in the industry, when industries that use a lot of sucrose, and they don't need to have it in solid form when it arrives at the factory, will ship it as a solution. because there's so little water in there, and it's more efficient to move liquids around. It's easier to move liquids than it is solids. So they can just pump the liquid anywhere they want in the factory, as long as the little bit of water that's in there doesn't affect their process. I've got a book. It's called "This is Liquid Sugar," and it talks all about manufacturing with sugar solution. But that's just one caveat. We still call water is the solvent because it was the major component when you started. You're adding sugar into the water. So we consider the water the solvent, even if sugar exceeds that amount. Okay. So now the color, you can get a color change when you add a solute to a solvent. The solute can be one color. The solvent can be perfectly transparent, clear, have no color whatsoever. And when you put them together, the interaction of those two, solute and the solvent, can actually change the color. You can put a perfect example. Let's see. Copper, I think that's 2+. Copper sulfate. Like this, the solid is a white crystal. Okay. As soon as you put it in solution, it turns a bright blue. And that's one of the ways we do a lab in general chemistry where we determine how much water is actually associated with each molecule of, or each formula unit of copper sulfate. And we take copper sulfate that's got water associated with it, and it's been dried down, but the water is still there. It's called waters of hydration. And we put it in a crucible and heat it up. And you can tell when all the water's gone because it goes from a blue crystal to a white crystal. But what we're looking for in a solution is you cannot see the particles of the solute in that mixture. Now, if they're small enough, you won't see them anyway. So there's a technique we use to determine if we have a solution or just a suspension, where you have the really, really, really small particles. And you think you've got a solution. The way to test it is called the Tyndall Effect. So you have your beaker here, and you have what you think may be a solution. So you get a bright light, and you shine that bright light in there, and then you look at it from both this side and that side. Right? So this side, either one, unless it's just completely opaque, either one, you're going to see light coming out this side. But if you look from this side, if it's a solution, you won't see anything in here. There's no diffraction of light off the particles. If it's a solution, that's the case. If it's a suspension, you will be able to see the beam of light going through the mixture. That's not a solution. Okay? We use that effect in one of my general chemistry labs too, because the end point is the formation of precipitate. But the precipitate is it's such small particles, by the time you see them with the naked eye, that you've gone past the end point. So we use the Tyndall effect to detect our end point. Okay. So you can have a colored solution as long as you don't see that, you check it with the Tyndall effect, you don't see the light beam in here when you shine it through, then even if it's got a color, it's a solution. It's transparent. Okay, general properties of a solution. They can have two or more components, right? you've always got to have the solute and the solvent, and you can have lots of solutes if you want. I mean, any biological fluid will have just dozens of solutes, right? Take a sample of your blood. Actually, your blood is an odd mixture. It's a suspension, it's a colloid, and it's a solution. It's all three together. So that's probably not a good example for our chemistry. It's a little too complex. But you can have more than two components, is the point. And you can have variable composition. What we mean by variable composition is for every unit of solution or solvent, whichever the case may be, you can have a varying amount of solute. And each solute can have different varying amounts. So the composition can vary all over the place within narrow parameters that are characteristic of each solute-solvent interaction. And what I'm talking about there is solubility. So some solutes, you can put only just a little bit in solution and it won't hold anymore. But with like sucrose, you can put a lot of solute in there. You know, just keep pouring it in and it'll take it. Now there are chemical reasons for that happening. Interactions between the solute molecule and the solvent molecule are so strong in the sugar water example that you get very strong interactions between the solute and solvent that keeps it in solution. Properties of the solution change with this variable composition. For instance, if you add, well, let's stick with sucrose. As the concentration of sucrose increases, you may notice that if you try to pour some out, the more sugar you have in there, the thicker it is. Viscosity changes. That's one physical property that changes with the percent composition of the solute. But there are other properties that will change also. Conductivity, for instance. If you put salt in water, just a little bit, it'll conduct some electricity. Put a lot more, it'll conduct electricity better because there are more ions available to transfer the charge from one electrode to the other. The solutes go into solution as individual particles, and they associate with the solvent in various ways. They could be atoms. For instance, you can dissolve some, some gases, noble gases as individual atoms. You can dissolve molecules, even gases like oxygen, which is diatomic, nitrogen's diatomic. They go into solution as individual molecules. Or sucrose molecules, they retain their identity in solution. They just associate with the solvent in such a way that they meet all the criteria for solutions. Or like sodium chloride, they can go into solution and break up into ions. And that's typical for ionic compounds. Sodium chloride is a good example. Potassium chloride will do it. Light salt. Copper sulfate, it breaks up into individual ions. The copper ion and the sulfate ion. So there are individual particles of each, depending on their nature. Are they molecular? Are they covalent bonds holding the molecule together, or are they ionic bonds? If the ionic compound goes into solution, it always breaks up into individual cations and anions, positive and negative. This is absolutely essential for a solution. When you say that the solute is solution in the solvent, then it is uniformly distributed. That's a homogeneous mixture. And it will not settle out over time. You can seal the jar, set it on your desk, and come back 100 years later, and it's still there, just like it is, no settling whatsoever. If it's a suspension, then the particles are large enough, they will eventually settle out. Okay, there's a special case in there, colloids, where the size of the particle is so small that the kinetic energy of the solvent molecules is sufficient, so they're banging into the suspended material, the atoms or molecules, and they're keeping them suspended, so they won't settle either. But they're not solutions. So there's kind of a middle ground there, the colloids. When you hear the word colloid, think Jello. Right? Jello is not a solution; it's a colloid. And you can separate the solute from the solvent by physical means, right? Depending on what type of solute you have, solute-solvent interaction. You choose the physical approach that will separate them. If the solute is non-volatile, like sugar or salt, right? If you leave those out on the tabletop in the container, either one of them, they won't evaporate. They'll just sit there. So in that case, then you can heat up the solution, the salt solution, for instance, and let's see, we did that, didn't we? Yeah, you can heat up that solution, and the water will evaporate, and you'll have your salt left over. That's a physical means of separation. So what that means is that the solute retains its identity in solution. Right? It doesn't react with the solvent in a way that will change it from one substance to another. There are some things when you try to put them in solution, there is a chemical reaction that they will undergo. And in that case, you may have a solution after the reaction, but it's not the solution with the substance that you put into it at first. A perfect example of that. If you take sodium, chunk of sodium, and you put it in water, it won't be sodium, it won't be like this. Doesn't happen that way because sodium will react with water. And when it reacts with water, it produces sodium hydroxide plus hydrogen gas. So this is your solution. Sodium hydroxide is in solution, which means you have sodium ions and hydroxyl ions, right? Because this is an ionic compound. Okay, so in that case, the substance you try to put in a solution changes its identity. It's not atomic anymore, it's ionic. Okay, so the solution you thought you might have, you don't have. You do have a solution, but it's not the one you started with. Okay. So if we were to take that solution that I just made with sodium and water and dry it down, what do we have left? When you remove all the water, you don't have sodium. You have sodium hydroxide crystals. Okay. Homogeneous mixture with 80 milliliters of water and 20 milliliters of alcohol. Which one's the solvent and which one's the solute? Well, by definition, the major one is the solvent, right? Water. And the minor component, alcohol, is the solute. Okay, I mentioned solubility before. Solubility is a term we use to describe how much solute can we put in solution. Right? Before, it won't take any more because there are limits. even with sucrose, there's a limit. Otherwise, we wouldn't be able to make rock candy. You ever had rock candy? That's good, isn't it? Very sweet. Well, they crystallize it out of saturated solutions of sucrose in water. And they just have a little seed, hang little seeds in there, and then they gradually, it's warm to begin with. And then they gradually cool it down. And as it cools down, it becomes less soluble. So it attracts itself to that seed of sugar and the crystal grows. I've used that before with other things, like copper sulfate's a good one. It makes nice big blue crystals. Okay, so solubility is a term that we use to express the maximum amount of solute that can be dissolved in a solvent. And this is dependent upon a number of things, but primarily upon temperature. If we're dealing with gases as a solute, then pressure comes into play. Okay. Most solids, if we talk about solid, and we're restricting our solute to water this time. Solvent is water. So most solids go into aqueous solution. As we increase the temperature, the solubility increases. And solubility is quantifiable. We can say, use any units you want. If you look at the CRC handbook of chemistry and physics, it will give you lists and lists of solubilities for compounds in water. Sometimes it'll use other solvents like ethanol, but it'll give you their solubilities in terms of grams of solute, grams of the compound per 100 milliliters or 100 grams of water. That's how it will list them. And it will give you a temperature. If it doesn't give you a temperature at all, then you assume it's standard temperature. And standard temperature is 25 degrees C for everything except for gases. When we talk about standard temperature for physical properties of gases, we're talking 0 degrees. But for everything else, solubility in this case is 25 degrees. So if they don't give you a temperature, it's 25 degrees. If they do give you a temperature, it'll be listed usually as a superscript next to the value that you give you for solubility. So many grams per 100 milliliters of water, and it'll have a little superscript temperature. But I said all that just to emphasize the fact that temperature, the effect of temperature on a solid going into aqueous solution is usually, for the vast majority of solids, as you increase the temperature, you increase the solubility. There are some exceptions where it goes the other way around, where you increase the temperature and you decrease the solubility. It's not easy. In fact, I haven't heard a good explanation for that. I think they're still working on the mechanisms. Got to get some graduate students, cheap labor to do that work for you. Whereas, by contrast, gases become less soluble as the temperature increases. Those are just blanket statements. If subsequent slides start to give us an explanation for it, fine. If they don't, then we'll just leave it at that. Most solids increase solubility with temperature. Gases decrease solubility with temperature. So when you're going to boil water, you put a pot of water on you're going to make spaghetti. So you got a pot of water on, you turn on the heat, and you stare at it so it'll take longer to boil. And eventually, what does it do? You start seeing gas bubbles, right? Those are not water molecules turning to steam. The first thing you see as you heat the water up is gases coming out of solution. As you increase the temperature, the gases are less soluble. So they come out of solution, they just form little tiny bubbles. And then eventually, after those disappear, then you get the water hot enough to boil. And then the gas that comes off is water vapor. Okay. So here are illustrations, and this table comes straight out of your book, at 3 different temperatures, 0, 50, and 100 degrees C, for these compounds in aqueous solution. And it looks like lead 2 bromide is more soluble with temperature. Silver sulfate is more soluble. Copper sulfate is more soluble. Sodium chloride is more soluble. And they have variable amounts. Like sodium chloride is pretty soluble to begin with. So increasing the temperature doesn't make it a whole lot more soluble. It's really dependent upon the solute-solvent interaction. Silver nitrate becomes more soluble. Cesium chloride becomes more soluble. And the solubility is extremely variable, right? Lead 2 bromide, you can only put a little bit in solution. This is in grams per 100 grams of water. So this is the way you would see it in the handbook, listed that way. And this is for practical reasons. If you're going to make a solution, you want to make a saturated solution, it's easier to say, all right, I measure out 100 grams of water, which is basically 100 milliliters. And then I put this many grams of the solute in there, I should get a saturated solution at these temperatures. It's easier to deal with that way rather than to use any other measure like, well, we're going to talk about it later. I'm starting to talk about molarity. We have to define it first. Calcium acetate is an example of a solute that is less soluble as we increase the temperature. You can think of it in these terms. This is not a really good explanation, but it is an explanation. When you do anything to a system, and we're going to treat this as a system, a solution. When you do anything to that system, it's going to tend toward the lowest energy possible. That's stability. All natural systems tend toward the most stable situation. So as we increase the temperature, its most stable situation is to have less calcium acetate in solution. That doesn't explain why, but it's sort of a, I don't know, rationalization of what's happening. Okay, effect of pressure on solubility. Solids and liquids, very little effect when you change the pressure over the solution. The solubility of liquids and solids barely changes. You might see some effect if the solute is particularly volatile. If you try to put something volatile in solution, like some of the alcohols, some of the aldehydes, some of the definitely ethers. When you try to put them in solution, then the head pressure may make a difference. But if the solid and liquid are, well, obviously the solid is non-volatile, but if you have a liquid that's reasonably non-volatile, then head pressure is not going to make a difference in solubility. Gases, though, pressure has a major effect on solubility. That's why when you grab a 2-liter pop bottle, it feels tight, doesn't it? There's the pressure inside, and that's keeping that carbon dioxide in solution. So when you open the cap, it pops because there's pressure. If you decrease the temperature of your whatever's in the container, the pop, then when you open the cap, it won't be as loud, it won't pop as much because there's less pressure on it. So that's why all my soft drinks go in the refrigerator first. I rarely open a can of any kind of soft drink, any pop, if it's room temperature, because the minute you pop it, you instantly lose a major portion of the whole reason you're drinking it, for the fizz. So I always put mine in the refrigerator first. And after I open a 2-liter bottle, cap it up, stick it back in the refrigerator. I don't leave it out. Okay. Now, here's the expression for the effect of pressure on solubility for gases in a liquid. This is Henry's law. And the temperature, now the temperature has to be constant. Right? If you change the temperature, then you're going to change the solubility of your gas in the liquid. But as long as the temperature is constant, then the concentration of your gas in solution is proportional to a constant, whatever the case may be. And it's different for each gas, for each solute system. And it varies with pressure. So notice that if you have this concentration like that, if this is a constant, then in order to keep that constant, I like to put the constant on one side of the equation. It's easier for me to conceptualize it. So if we do this, right, just solve it for the constant. Now, what does each one have to do to keep that constant? If this goes up, that has to go up. If pressure goes up, concentration goes up, right, in order to keep this constant. And I think I explained when we talked about gas laws, the before and after concept. So if you know if the temperature and the moles are constant, then you can watch the relationship of pressure and volume. Remember that? Okay. So we can use that concept here. If this is equal to a constant and the temperature doesn't change, then these two values are equal to that constant. Then if you change the pressure, if you change the pressure, then you're going to get another concentration. So before and after. So you can use it that way, rather than trying to figure out what the constant is. Right? Because you may not need to know what the constant is. You're just doing a before and after situation. But that's Henry's law. Okay. Here's a saturated solution. And by definition, it contains the maximum amount of solute that can be dissolved at this temperature. Here's the saturated solution. And what you're seeing in this illustration is, here's a solid, right? It's got regular arrangement of these atoms, molecules, ions, whatever the case may be. And these are the particles that are in solution. In a saturated solution, if you have some of this solid left over in that solution, then what's happening at the interface between the solid and the solution? What you're seeing is, well, macroscopically, you're seeing nothing. It looks like it just sits there and doesn't change. Microscopically, what's happening is you're having some go into solution and an equal number returning to the solid. That's an equilibrium situation. As long as the rates of dissolution equals the rate of precipitation, then you have an equilibrium. And that is an indicator that you have a saturated solution. Let's see. Did we do, rather than ask, let me just look. Okay, we are going to do this later. Le Chatelier's principle. We're going to look at an equilibrium situation where you have saturated sodium chloride. Well, I may be able to show you this if it's not already filtered. The solution that I made for saturated sodium chloride, I heated it up and I put in excess sodium chloride into the water, and it all goes into solution at that temperature. And then I set it on the bench and let it cool down. When it cools down, it becomes less soluble. So the extra sodium chloride now at the lower temperature settles out on the bottom of the flask. And now I know at that temperature that it is saturated. So if I don't want any solid carried over into an experiment, I just have to filter it. But that's guaranteed that it is saturated at the room temperature of the lab at that point. If you've got some solid in here, you're having the exchange between the two, you know it's saturated. Now, one thing I didn't mention is when you set that solution that I heated up with extra sodium chloride in it, you set it on the bench and you don't disturb it. We don't have an earthquake to shake it. Then as it gradually cools, there's a good chance that it will retain more solute in solution than you would expect at that temperature. In that case, it's supersaturated. One characteristic of supersaturated solutions is they are very unstable. All you have to do is look at them cross-eyed and the extra will precipitate out. Or shake them actually. Or reach in and scratch the side of the inside of the container with your spatula. You just provide nucleation sites, we call them, and they will drop out a solution like that. Okay. Any concentration that's less than saturated is unsaturated. That's pretty much a no-brainer. Concentrated solutions and dilute solutions, these terminologies, concentrated refers to a large amount of solute, and that's relative to its maximum amount. So if it's a large amount, it's close to but not quite saturated, then we say it's concentrated. But if it just put a little bit in solution, well away from its saturation point, that's dilute. Okay. So the point of this slide is this solution is dilute, right? And you can tell from the color that it's dilute. And we set it out on the bench and let the water evaporate. The solute doesn't evaporate. We're reducing the amount of solvent over time. So now we have a concentrated solution. And you can tell from the color that it's bluer, and that's an indicator, at least for this compound in aqueous solution, that's an indicator that it's more concentrated. And actually, photometrically, you can quantify this. Right? If you have a spectrophotometer at a given, tuned to a given wavelength, it will be absorbed. The light will be absorbed when you pass it through a standard width. Take a sample out, standard width, which is usually 1 centimeter. And it'll give you a certain absorbance, amount of light absorbed through that solution. And then you take this one and put it in there, there'll be more light absorbed. Okay. So that's one way that you can quantify, in relative terms, the difference between the two. We do an experiment that uses that too in general chemistry. You're missing out on a lot. You can take the 2-semester version. Okay. Up to this point, we've focused on aqueous solutions where water is the solvent, but you can have non-aqueous solutions. Even solid liquid or liquid-liquid, you can have non-aqueous solutions. And those are particularly important for certain types of chemical reactions. Organic chemists love non-aqueous solutions because water, in many cases, tends to react in ways that they don't want. So you get your reactants in solution, but it's not aqueous. You put it in a solvent that will not participate in the reaction. Solubility of a gas in water. How does temperature affect it? Increase the temperature, decrease the solubility. Pressure, increase the pressure, increase the solubility. So there it is. Okay. I've said this before and I'll say it again. Nature just does what it does. Here's a case where we have to conceptualize the dissolution process, try to make sense of it. And it comes in 3 steps. The first step needs another marker. See if I got one that'll work. Need some help. That's a little better. Okay, 3-step process. 1, the solute is separated from the solvent before we put them together. You recognize that the solute molecules have an attraction for one another. Right? If it's a very strong attraction, there'll be a solid. If it's a little weaker attraction, there'll be liquid. And if there's almost no attraction, it'll be a gas. But there's still some interaction, some attraction, some forces that have to be overcome. Because remember, a solution has individual particles of the solute in the solvent. Right? You got to get them apart. So here we have to break the solute bonds. This is not behaving either, is it? It's not going to show it very well. You have to break the solute bonds. This is, we have to add energy to it. And the term for that is endothermic. Right, endo means into. So you have to add energy to break those bonds. Step 1. Step 2, which is going on simultaneously, is the solvent also has intermolecular forces that are drawing those molecules together, and we have to break those bonds too. So here we have to break the solvent bonds. And when I say that, the intermolecular bonds, those between the molecules, not the intramolecular bonds that hold the molecules together. You don't break those, that's a chemical reaction. But this, you break the bonds that are holding the solvent molecules together. And this is also endothermic. Sometimes this is called make a hole in your solvent. And the third is we reform bonds between the solute and the solvent molecules. Solute and solvent. Is that still picking it up? Yeah. This is exothermic. Okay, so you put energy in, these two, and you get some energy back. Okay, so the balance among these 3 processes determines whether your overall dissolution process feels cold or feels hot. If it feels hot, then it's giving off more energy here than you put in there. If it feels cold, then you had to put more energy in here to break those bonds than you get back when the solution is formed. Okay, so the overall endothermic, if these guys win, overall exothermic, if this one wins. Okay, and you can see that in any hospital setting. You got those little bags of water and a little capsule inside. You break the capsule and mix it up. Some of them get hot, some of them get cold. And they're using two different dissolutions here. Well, it's the solvent's the water always in those cases, but it's a different solute. And one solute lets this one win, the other solute that one win. But you can only use them once, right? Here, use once and throw away. Okay. So what affects the rate of forming a solution? Well, the most obvious one is particle size. The smaller the particles, the more surface area you have. And this would be particularly applicable in a solid solute in a liquid solid. Doesn't make any sense if we're talking about liquid and liquid. Particle size would make a difference in the speed at which the solution is formed. So if you put a big old chunk of rock salt in a container of water and let it sit, it's going to take a while to go in solution. But if you take the same mass of salt from your shaker or from your container and pour it in there, it'll go into solution a lot faster. There's more surface area. So these interactions here occur at the surface of the solute. You can also increase the speed with agitation. So what that does is, if you look at a particle of, say, sodium chloride, it's going to be cubic. You know that because if you spill some salt on the table and take a magnifying glass and look at them, just a bunch of little cubes sitting on them. It doesn't matter how big the crystal is or how small it is, it's always cubic. That's actually an indicator as to how the sodium and the chloride ions arrange themselves in that crystal lattice. But if this is a big cube like that in water, sodium chloride, then as the sodium and chloride ions are taken into solution, they form a gradient around that cube. So immediately at the surface, the concentration of sodium and chloride at the surface in solution is very high. So remember when we had the particles going backwards and forwards from solid in solution and precipitating? That rate depends on how concentrated are these particles in that immediate environment. They're very high, then the rate of dissolution slows down because you get some of them returning, right? So they're offsetting the dissolution by returning. But if you agitate it, now you've got fresh dilute solvent interacting with the interface. And the process of migration of these ions into solution is faster because they're seeing fresh dilute solution as you agitate. We get a similar effect with the Windshield Factor. So why is a Windshield Factor so dangerous when the temperatures are, right at freezing? If the wind is 30, 40 miles an hour, you're going to freeze a lot faster than if the wind is calm. If the wind is calm, then you build up a layer of heated air around your body, right? You don't lose heat as fast. But if there's wind blowing, there's unheated air coming in and replacing it constantly. So the transfer of heat from, which is always the case, high temperature to low temperature, is going to cool your body faster. Similar concept here. Another idea. You've ever heard of countercurrent exchange? It's common in engineering. It's very common in biology. Birds, for instance. If you look at a bird's lungs, they're passed through. A bird's lungs are, let's say that's a bird's lung, and here's his head, beak, right? He takes in the air, it goes through the lungs, right? Just like it would in ours, and oxygen goes into the blood, right? But he's got a bag down here, and this is the bellows part. This bag expands, pulls air through, and then it contracts and pushes air back. It goes through, gives up some oxygen into this bag, and then while it's doing that, there's more blood, unoxygenated blood that comes in here. And then when he blows the air back, it picks up more oxygen from there. Right? So for mammals, for humans, for instance, there'll be 21% oxygen in the air. We draw it into our lungs. When we expel it, you measure it, it's about 10% expelled. But for a bird, it's going to be closer to 5 or 4%, because they picked up some on the way through and picked up some on the way back. It's more efficient. That's why birds can fly at 15,000 feet. They can extract more oxygen from the air than we can. At that height, we go hypoxic. Okay, that's countercurrent exchange. Right? Agitation. Okay, that's where I left off. Agitation increases the rate of dissolution. Temperature, usually for solids in liquid, will increase the rate of dissolution. Then there's one that we need to spend a little bit of time on, the common ion effect. And as the name would indicate, these are for ionic solids that are we're trying to take into solution. And let's confine our arguments to aqueous solutions here. So if we've got our sodium chloride crystal, right, and we've got water here, then if there's just water and there's just sodium chloride, then you can get sodium and chloride to a certain extent going into solution. No problem. But if you put a pre-existing sodium chloride solution in there and try to dissolve some more of this, right, you've got these chloride and sodium ions that are trying to go back into that crystal lattice, and they're slowing down the process of dissolution. Okay, these are common ions. This sodium ion is common to that crystal, and this chloride ion is common to that crystal. If we had calcium ions in solution, it wouldn't matter, because this ion is not common to the solute. It's only when the ion is common to the solute that it changes the solubility of the solute. Okay? And if you took general chemistry, we've worked problems where you quantify that fact. But for now, you have to take it at face value. Okay. General rules for solubility. If the Well, let's go to the rule of thumb first, right here. Like dissolves like. What we mean by that is in terms of polarity. Like dissolves like. So this would be the solvent. Solvent dissolves solute. If, sorry. I forgot to turn on my silent time. There it goes. Didn't block any messages now. So if the solvent dissolves the solute and they're the same polarity, then the solvent and the solute are more likely to form a solution. So if this one is polar solvent and this is a polar or ionic, as a matter of fact, solute, more likely to form a solution. If this is nonpolar, and this one is nonpolar, you're more likely to form a solution. But if this one's polar and that one's nonpolar, or this one's polar and that one's nonpolar, you're less likely to form a solution. Or if you do form a solution, there'll be very much reduced solubility. That's what like dissolve like means. Table 8.2, is that what this one is? Oh, it doesn't have a table on it. Oh, this must be table 8.2 in your textbook, and this is the chart that I gave you. I don't know, I haven't looked at the textbook in a while. Does 8.2 look like the one I gave you?
Yeah, I'm pretty sure it does.
Okay. Okay, these are solubility rules. Now, if you were in general chemistry, you'd probably have to memorize them. Let's see. But in our case, use the chart to tell you if a particular ionic compound is soluble in water. You just follow the cations across the top and then the anions down the side and go over to where they meet. And if it's a clear box, they're soluble. And if it's grayed out, they're insoluble. Now, these are relative terms. Solubility can be quantified in terms of how much solute goes into a certain amount of solute in solution. So when we use this chart, we're also saying that if we say insoluble, it may be slightly soluble. But for our purposes, slightly soluble is insoluble. If it says soluble, then you can get a substantial amount of solute in solution. I'm going to skip this because let's see, do I have here are the rules. Okay. These rules are also reprinted at the bottom of your solubility chart if you're interested. And if you use it enough, these things will become ingrained. But the first rule is compounds of group 1 elements, the alkaline metals, and ammonia are all soluble. There are no exceptions. Anytime you have these cations with any anion, they are soluble. And the other thing is these are arranged in hierarchy, right? So if you have say this one where carbonates are generally insoluble, carbonate's an anion, and it's a carbonate of one of these, like potassium carbonate, that one takes precedence. The one above wins. So carbonates of potassium ions are soluble. If you don't find one of these to win, then the carbonates are insoluble. Right? So if we don't have, say, calcium carbonate is insoluble. Right? There's no calcium up here. There's no calcium above it anywhere. So calcium carbonates are insoluble. Chromates are insoluble. Phosphates are insoluble. Sulfites are insoluble. Right? Unless you make one of these compounds with one of those cations, then it will become soluble. See what I mean? The tiebreakers are above. Let's see. As far as rules go, focus on this one. If I haven't said it before, mercury is a funny ion. Mercury is always 2+. If it's by itself, that single atom is a 2+ charge. But if the atom is a 1+ charge, there are two of them, right? So the ion for mercury is always 2+, but the charge on the individual atoms, in this case, is 2+, and in this case is 1+. Right? So mercury is funny that way. Whenever it's in a compound, it's either this one or that one, but there's always a 2+ charge involved. Sometimes there are two of them, sometimes one. I need to get another mark. This is irritating. Let's see here. Oh, I bet this will work. Okay, so those are the rules. But this is what you're going to be relying on. And you'll have this available in the back pages, the useful information for the exam. You don't have to just learn how to use it. Right? Here's your cations across the top, your anions down the side. And all you have to do is like you're using well, I don't know, people don't use road maps anymore, do they? They always have the mileage chart in them where you can go from where you are to where you're going, and then you match them. That's how many miles. So you use it the same way. You go your anions, cations where they meet. Oops, insoluble. Okay. There are some exceptions in here, like these, and they're described down here. These guys react with water, so you don't form sodium oxide. Sodium oxide in water reacts with water, kind of like the sodium I showed you before. If you try to put this one in water, it reacts to form sodium hydroxide. So that's why those asterisks are there. Special cases. I'll try not to give you any of those. Okay. So the greater the difference between solute and solvent polarity results in less solubility of the solute. If they're close to each other in polarity, then they're more likely to form a solution. Now, we did polarity earlier, didn't we? Yeah. Okay. So remember, you need, in order to determine the polarity of a molecule, you need polar bonds, and then you need to know the geometry to tell you if it's polar. Well, you know water is already polar. Like that. So it's going to be like that. So water is, they call it the universal solvent, but it doesn't dissolve everything because it's polar. Sometimes you need a polar solvent, like I don't know, hexane. It's a good polar solvent, or octane, like out of your gas tank. They're nonpolar, so they would more readily dissolve nonpolar solutes. Of course, there's a special case where you want to wash your clothes in water. but most of the soiling of your clothes is oily. It comes off your skin, comes off the environment. It's non-polar. So how do you bridge the gap between non-polar and polar? You need another molecule in there to help you. That's where soaps come in, detergents come in. They have a polar end and a non-polar end. So the non-polar end dissolves in the oil in your clothes, and then the polar end makes its association with water. So that's how you bridge the gap. In fact, it's a little more complicated than that. They form micelles, which are like spherical things where the, let's say you have a droplet of oil coming from your clothes. Then you have your polar end, let's say it's negative charge. And then you have the non-polar end. Dissolved in the oil. And then the water forms the bonds with that end. And that's how you get stuff in solution, so you can wash them out of your clothes. Not to spend too much time on it, but soaps, which are saponified fats, you take lye. Got any older relatives that still make their own soap? Yeah, you take lye and lard, or fat, and you mix them together, and it makes soap. The problem is, it's got an ionic end. And as long as it's combined with those alkali metals, like sodium, potassium, rubidium, whatever, then it'll go into solution pretty easily. But if you get any calcium or magnesium or aluminum in your water, or iron, which West Virginia has in abundance in their groundwater. If you pull up well water that's got all that stuff in there, it tends to form a precipitate with your soap. We call it scum. And it can mess things up. So pure soap is good as long as you don't have those divalent or trivalent cations in your water. Now, I lived for 13 years in Baton Rouge, and our water was soft. Its primary cation in the water was sodium. So it felt like you weren't getting clean. Right? It's just slippery, but it was great for your hair. And it wouldn't form scum. And that's where detergents come in. Right? They're specially engineered molecules that are non-ionic, but polar on one end. So they don't interact with those cations to form the scum. So there you go, problem solved. Okay, which of the following ions that are generally soluble in water form compounds with iron? Okay, so compounds with, lead. Compounds with lead that are soluble. So we get our chart, and we find lead across the top, and then we go down until we meet sulfur, chlorine, nitrate, sulfate, and say, are they soluble? So if you do that for sulfide, lead 2 sulfide is insoluble, forms a solid. Lead 2 chloride, that's insoluble. Lead 2 nitrate, soluble. All nitrates are soluble. And then sulfate, it's insoluble. And then the last one is a ringer. It's stupid. You don't form compounds between cations. Okay, so the answer is nitrate. So if you want to get lead into solution for some chemical reaction, lead 2 nitrate would be a good choice. Okay, how do we express this variability of composition? Different units of concentration are used, and we're going to focus on 2, percent concentration and molarity. Maybe we do. I don't know if we need that one. Let me see if we need that one for our labs. Yes, we do. Osmosis and dialysis. We'll need this one, molality. So 3, percent composition, molarity, and molality. Molarity and molality are related. So once you understand molarity, it just takes a tweak to understand molality. Okay, usually when we say percent, in this context, we mean percent by mass. In other words, mass of solute per unit mass of solution. So say 100 grams of solution will contain, for argument's sake, say 5 grams of solute. That would be 5% by mass. That's the Achilles heel of percent. And if I haven't said it before, I'll say it again. Percent is a dimensionless value. It just means parts per 100. It doesn't say whether the parts are relative to mass or volume or what they are. So you have to, if it's not implicit in the problem that's being proposed, then it has to be given. What type of percent is it? Vinegar. If you look at a bottle of vinegar, it'll say 5% acidity. And I always wonder, what does that mean? Right? Well, I assume it's relative to 100% acidity. So 100% acidity would be 100% glacial acetic acid. Right? And you can get that in a bottle. It's dangerous. It's flammable because it's an organic compound, but it's also, it's a weak acid. Right? We talked about that before, right? Acids and bases. It's a weak acid, but it's so concentrated that there's enough hydrogen ion in solution that it will cause damage to your skin if you spill any on yourself. But what does that mean? Well, it needs to be defined. So when we say percent concentration in this context, we have to say what it is. Is it by mass? Is it by volume? Or is it by mass volume, which are the most common 3 types of percent? All right, so percent by mass for our solution would be mass of the solute per 100 grams of solution. So once you get them together, and this makes it easier to calculate the percent because mass doesn't change with temperature. Right? When you have a gram of something, you got a gram of something no matter where you are in the universe. So the mass of the solution would simply be the mass of the solute plus the mass of the solvent. See if we got a sample problem. Yeah, we do. Percent by mass, calculate that for 5.5 grams of glucose. In how much? In 78.2 grams of water. There you go. The total mass of the solution is this, that plus this, times 100. So that should give us 6.6%. Percent by volume. Percent by volume is useful for liquid solutions. But the temperature comes into play here because when you change the temperature, you change the volume of the liquid. 30 milliliters of methyl alcohol in enough water to give 435 milliliters of solution. In this case, it's important to say what's the volume of the solution, because when you add a solute to a solvent, the volume is not necessarily the sum of the two, right? Remember when you pull them apart to make a hole? Sometimes you make a hole, and then when you get the solute interacting with the solvent, the hole shrinks to smaller than it was before. So you can put 30 milliliters of solute in, say, 485 milliliters of solvent and put them together, and they end up with 435 milliliters of solution. So this was out of necessity. We had to tell you what the final volume was. And in this case, ethyl alcohol in that arrangement gives you 6.9% volume, or ABV. Right? You'll see that on wine bottles and any booze bottles will have it. ABV, alcohol by volume. That's what that means. 6.9%. That would be maybe a pop wine, or that's a little more, that's a little excess for beer. I think beer is 6.4% typically. Okay. And then mass volume percent. If you have so many grams of your solute in volume of solution. Now this is different than the earlier one where we had solubility in water, so many grams per 100 milliliters of water. Right? That would have to be specified also. But in this case, mass volume percent is the volume of the solution. It's important for practical purposes to have this value be volume of solution. Because if you have a value for this and you extract from a stock so many milliliters out of that stock, then you can prorate it. It's a ratio. You can say, then I know how much of this I have in that solution. Whereas if you put grams per volume of solvent, then you pull out 100 milliliters of your solution, you don't know what you got. Okay, so let's see. Conversion factors. Oh, yeah, good point. When we work problems, we've got a ratio in our solution of solute to solution. And whenever you have a ratio like that, it depends on the problem, but one of these could be a conversion factor, right? All you need is, if we have so many grams of sodium chloride and we know the concentration is this, then we can say, how many grams of solution will I need? Right? You can use any of these as conversion factors, right? Anytime you have a ratio, it can substitute as a conversion factor. Just like molar mass, right? Grams per mole can be used as a conversion factor. Did I lose anybody there? That makes sense. Okay, good. So if we have a mass percent concentration of 10%, what does that mean? 10% contains 10 grams, okay, of solute. That's good. Solute, right? 10 grams of solvent, 10 grams of, no. B and D are out. It has to be A or C. Because we're saying 10 grams of solute and 90 grams of solvent? Yes. Because the total has to be 100 grams. So our answer is A. How many grams of sodium chloride are needed to prepare 150 milliliters, 0.9% mass volume sodium chloride? Let's see, do I have this one animated? No, I don't. Okay, so how many grams of sodium chloride? We're starting with 150 milliliters of 0.9%. Right. So will our value here do the trick? Mass volume, that's 0.9 grams of sodium chloride per 100 grams of solution. Right? 150 milliliters of solution, 0.9 grams per 100 grams of solution. Okay. That's not going to hit this. These won't cancel. So we have to say to ourselves, is this solution dilute enough so that we can treat it like water? And I'm talking about density. So the density in this case would be milliliters, grams, 1 gram per milliliter for water. So if this solution is dilute enough, by the way, you've seen that before in a hospital and printed on a bag. It's normal saline. In other words, it's isotonic to your tissues. And if you give the patient this solution, it won't cause their cells to rupture or shrivel up. And you give this to a diabetic. Right? There are other types of isotonic solutions like lactated ringers. But if you give that to a diabetic, you're going to drive their sugar through the roof and be in big trouble. Okay, so here I converted milliliters to grams of solution. And then now that cancels. And now we can say 150 divided by 100 times 0.9. And that should give us 1.35 grams of sodium chloride contained in that solution. So there was, the trick to that one was assuming the density of this solution is the same as water. Just in case you're interested, this solution may be isotonic to your tissue, but it gives you about twice as much sodium as you need. And it gives you about, I forgot, I looked it up one time. It's like between 50 and 100 times the chloride that you need. So you don't want to give this to your patient for an extended period of time. Just to replace their fluids, okay. But you can drive their ionic balance out of whack really quick with that solution. Okay, molarity. This is used a lot in chemistry. The reason being that when you talk about reactions, remember, reactions are moles to moles. When we have our balanced equations, moles to moles. So if you have a solution that you're reacting two solutions and you put them together to react, and you know the concentration, and you know the volume, then you can instantly calculate the number of moles and go straight from moles on one place to moles somewhere else in the balanced equation. So this is extremely useful for chemical reactions, molarity. And it's abbreviated, the big M. And the big M is good because there are no big M's on the periodic table. And it's always moles of solute per liter of solution. That's what molarity means. So notice if we have a value here for molarity and we know the volume, say we have 0.15 liters, right, times that, that's equal to the number of moles. So if we know the amount of solution we have, then we can calculate the number of moles that we possess also in that volume. The problem is this one right here. Temperature sensitive. Okay. As long as the temperature is really within 5 or 6 degrees of the temperature that you made the solution, then you're probably pretty safe, especially with water. Okay, definition of molarity, moles of solution per liter of solution. Moles of solute, excuse me, per liter of solution. So if we have 1 mole of sugar in 125 milliliters of solution, we can calculate the concentration. This needs to be liters, right? So move the decimal 1, 2, 3. 0.125 divided into 1. And that's 8 molar for this sucrose solution. Let's see. Okay. 10:30. You need to go in the lab at 11, right? Yeah, maybe we will stop here when we finish this section. Okay. If you have a 10 molar sugar solution, what volume of the solution do you need to have 2 moles of sugar? Well, we go to the definition, right? The equation. Anytime you've got an equation, you can solve problems with it. We want to know what volume of the solution do you need. So if we solve for volume, then we need moles divided by molarity. Okay, swap places here. And then we can put in 2 moles divided by, only 1, 10 molar. So what does molar mean? If you're going to cancel units, sometimes it's useful to convert. So instead of putting a big M here, I would put moles per liter. Then we know that this mole cancels that mole, and the denominator of the denominator is the numerator. So that liter comes up here, and that's 0.2 liters. Or how many milliliters would that be? 1, 2, 3, 200. There we go, solve for that. Some of them I have animated, some of them I don't. That's not right. That should be moles per liter. Let's see, 6. Oh, I got it marked here, but I didn't correct it. I think what I needed to do here was put a big M. Okay, now we will make things complicated. Consider 2 separate solutions, sodium hydroxide and potassium chloride, made by dissolving 100 grams of each in a solution that final volume of 250 milliliters. What's the concentration of each in molarity? Okay. 100 grams of sodium hydroxide will be a certain number of moles. 100 grams of potassium chloride will be a different number of moles. Right, so you know the molarity is going to be different. It just depends on calculating the number of moles of each. Right, so did I? Okay, there we go. Sodium hydroxide. Here's the molar mass of sodium hydroxide. So we convert that to number of moles. And then we have moles divided by liters. Let's see. That's not right. You divide by the number of liters. So this is going to put liters up here. That needs to be inverted. Put liters on the bottom, doesn't it? Anyway, the answer's right. It's just the graphic is wrong. Oh my goodness. This needs to be switched. I got a couple of fixes to do there. Probably would have been simpler just to say 1 over 0.250 liters. There you go. They'll put liters on the bottom, moles on the top because grams cancel. And that will give you molarity. So 10 molar for sodium hydroxide and only 5.37 molar for potassium chloride. So you got the same mass for each one, but you got different moles. Give you a different molar solution.